So she is a graduate of Tel Aviv University. She actually took 1 or 2 classes with me, I think. So it's really a true pleasure to welcome Karen, who will be talking more about spin-orbit coupling.
Which means that all my mistakes are because of...
I'm responsible for all the poor education, yes. But only in classical mechanics.
Uh-oh. Okay, thank you. And thank you for the opportunity to come and talk here. And I think the work that I'm going to present to you is quite related to what we had in the previous talk. And when we are thinking about superconductivity and spin-orbit coupling, is actually the last recent years, or actually for quite a time, we know of many materials and many systems and different systems where we see superconductivity in the presence of spin-orbit coupling. It is well known that in many strongly correlated systems we can see such effect. Nowadays, in various topological superconductors, spin-orbit coupling and superconductivity are intertwined, and as we heard before, at oxide heterostructures. Now, there are many effects that are coming because of the interplay between superconductivity and spin-orbit coupling, but I'm going to focus on one part of that, and that is the effect of either external magnetic field or internal magnetization. And we know now on more and more materials where superconductivity in the presence of spin-orbit coupling appears in the vicinity of magnetic transition. So here, for example, it's europium irradiate, where upon applying pressure, they can see that they have 2 transitions between 2 ferromagnetic states, strong and weak ferromagnetic state, and at the end, they see superconductivity. Or, as we had in the previous talk, where superconductivity is present in the background of some magnetic order. It seems to be that this magnetic order is actually very inhomogeneous. However, there is magnetic order in the system, and we have superconductivity and spin-orbit coupling. So now the question is what this interplay between 3 things, superconductivity, spin-orbit coupling, and ferromagnetism can do to the phase diagram of such system. So let me start by thinking about not fluctuating magnetism, but just constant magnetic field, external or internal in the system. And one of the things, as we also heard in the previous talk, that happens when we have superconductivity and we apply parallel magnetic field, which means just a Zeeman magnetic field in the system, is that the critical field, the critical Zeeman field, change as a function of the spin-orbit coupling. And here it is shown in a nice experiment. Basically, they were taking films of beryllium, thin films of beryllium, depositing gold particle on top of them to induce spin-orbit coupling in the system, and measure the critical parallel field as a function of the thickness of the film. The thinner the film, the stronger the induced spin-orbit coupling of this system. And what they observe is basically that the critical field grows here linearly as a function of 1 over the thickness, or as a function of the strength of the spin-orbit coupling. Another measurement that is done on superconducting films with spin-orbit coupling was actually done both on LAO-STO system and films of lead, and they were showing exactly the same effect. So here you can see measurement of the resistance as a function of magnetic field above the critical field. And what they observe in this measurement is that as they are applying magnetic field, the resistance goes down, and actually there is a re-entrant effect back into the superconducting film. We can summarize that by looking at how Tc is changing as a function of magnetic field, and it actually grows as a function of magnetic field instead of going down. Now, one can imagine that in both these kind of systems, so we said it's LAO-STO and lead, we have strong spin-orbit coupling. So one can imagine maybe there are magnetic impurities in such system, and what the magnetic field does is basically to align the magnetic impurities and turn them into regular impurities. And since from the previous measurement we know that the system can survive up to very high magnetic fields, so basically the entire effect is just to eliminate the magnetic impurities. So they were checking that. They were actually adding magnetic impurities into the system, and they were checking TC as a function of the doping with magnetic impurities. So basically, as we expect, as the magnetic impurity doping level grows, TC is going down. But what happens now when we apply magnetic field? If this scenario is correct, basically when you apply magnetic field, it will grow further and further the larger the amount of doping is. So here we can see what happened without doping. The magnetic field grows. With a little bit of doping, TC goes a little bit lower, and also the change in TC goes lower. As they are further increasing the doping with magnetic impurities, they can see that the growth in TC goes down and eventually just disappears. And that tells us that actually that is not an effect of magnetic impurities, because just adding more magnetic impurities, we should see just larger increase in delta TC. However, that's not really the effect. Okay, so we have two puzzles, and one is why we see the growth in magnetic field as a function of the critical field, as a function of spin-orbit coupling, and the second is why TC grows. So let's look at a generic model for electronic system with spin-orbit coupling. So first I will look at just parabolic band. And that will be our Fermi surface. In the presence of this parabolic band, it will be doubly degenerate because of spin. I'm adding spin-orbit coupling, and the effect will be to split the electronic spectrum, to split the Fermi energy, and we have two bands where basically the direction of the spin is coupled to the momentum of the system. Now we can ask what happens when we add superconductivity to such system. So regular S-wave type superconductivity, in terms of the new band, is basically going to be pairing in the minus band. That looks like actually chiral p-wave superconductor, but it's not really important. Pairing in the second band, which is also looking like a chiral p-wave superconductor, but with opposite chirality. So altogether, it's just a regular S-wave, nothing unique in such system. So as long as we don't have magnetic field, we consider the pairing with spin-orbit coupling, with that spin-orbit coupling, doesn't do anything, actually. Now let me add magnetic field to the system. Parallel magnetic field, so Weizmann-like. The effect is basically to shift the Fermi surface. One Fermi surface was going up, the other one was going down, and now the spins are no longer perfectly aligned with the direction of the momentum. So now what happens if we are trying to pair electrons with momentum k and minus k? We can see that here, the spin are no longer antiparallel, as in a regular case when we have just magnetic field in a superconductor. On the other direction, we can see that we cannot put both electrons on the Fermi surface. However, if we will try to pair electrons with finite pair momentum, we can see that the electronic spectrum for electron with momentum k plus q over 2 and minus k plus q over 2 only differ by this value. If we can set this value by tuning q to be 0, there is no effect of magnetic field on the system. Basic, oh, the angle around the Fermi surface. But since it's just multiply everything, the value of q, if we set it in such a way that q is just eliminating the second term, there is no effect of magnetic field in the system. However, there is a small problem that we have plus and minus that just refer to the two bands, and therefore we cannot eliminate the effect of magnetic field from both bands, but only from single band. So if I'm choosing q to be just canceling for the minus band this term, we will see that the surface of pairing of the larger Fermi surface becomes perfectly, again, as if we don't have magnetic field in the system. However, for the lower band, everything becomes a bit worse. But since here the density of state is very different for the large Fermi surface compared to the small Fermi surface, as long as energetically it helps us more to pair electron with finite momentum on the outer Fermi surface compared to the energy loss of the small Fermi surface, we will get superconductivity, which is at just finite momentum pairing. And from that, we can ask what will be the critical field. And the critical field of the system is going to be enhanced by a factor which depends on the ratio between spin-orbit coupling and the bare superconducting gap. For example, if we think about the LAO-STO, that's a factor of 2 orders of magnitude. There is a power there, which goes a matter of details. So let's say 1/2. It can increase the critical field by an order of magnitude, for example, for the LAO-STO. And what we are getting here is a unique superconducting state, which is what many times referred as the FFLO, the full differential Larkinov-Chinnikov state, where the order parameter is actually as a finite phase in it. Now, we can understand from this kind of explanation how, in the presence of spin-orbit coupling, we can get this large enhancement of the critical field. However, if we are looking at TC, it doesn't explain us anything yet. TC should still go down as a function of magnetic field. Just that instead of terminating at some low field, it terminated much higher field, at least in this kind of mean field type of consideration. So if we want to look at what magnetic field can do, and that to TC, and that was our motivation, we were asking ourselves what happens if we have magnetic fluctuation in the system, as we do have in several of these systems, for example, in the LAO-STO. So let's see what happened. We will look at some kind of macroscopic picture of the free energy in the presence of both superconducting order and magnetization. And when we are looking at the free energy of such systems, so you can recognize regular, just a kind of a phase-only free energy, you can just see the regular phase stiffness term. But we have a new term here that doesn't appear in a regular superconductors. And this new term is due to the spin-orbit coupling. It's proportional. Its coefficient is proportional to the spin-orbit coupling. And it basically couples the magnetic field, which is here the total magnetic field, either external or any kind of magnetization field, to the gradient in the superconducting phase. Now, in addition to these two terms, we should have just the magnetization, the mass of the magnetization fluctuations that we consider, but also just the spin susceptibility of the system. Now, we usually know that in regular superconductor, spin susceptibility goes to 0 at the deep in the superconducting phase. And that is another unique thing for systems with spin-orbit coupling, is that actually magnetic susceptibility doesn't change much inside the superconducting phase. And we can see that basically it can get a bit anisotropic. It will be different for xy plane versus the z direction if you assume that the spin-orbit vector is in the z direction. However, it's still very far from being 0. It's very close to its normal value. And that's something that people measured. For example, in this material, this cerium, iridium, silicon, it is known to be a Rashba type of spin-orbit coupling system. And they were looking at the night shift or the spin susceptibility in 2 different directions, in the c-axis and in planes. And they were looking how it changes. They are going below TC, and you can see more or less stay as it is in the normal state of the system. And that is because of the spin-orbit coupling. And that is very important in our system because obviously spin susceptibility will go to 0, magnetic fluctuation cannot do much. They can destroy the phase simply, but not more than that.
But spin triplet will also give you something like that.
Yes, definitely.
So you need to compare your results to a possibility of spin triplet.
Yeah, no, definitely. So we were looking at spin singlet, first of all, assuming, looking into account the fact that...
In this paper, they predicted a spin triplet.
They did. But it is correct, but that in general, I mean, there are a few questions. Spin triplet superconductivity, even in the presence of spin orbit or not spin orbit, is very sensitive to disorder. While here, the spin singlet is completely immune to disorder. And at least for the LAO-SDO, you would assume that there is enough disorder in the system that probably spin triplet is not very favorable. But also in the case of spin triplet superconductivity, TC should not go up. It's indeed more immune to magnetic fluctuation or any kind of fluctuation and to magnetic field, but it still should not increase TC. Okay. We can even simplify further this kind of free energy and look at the continuum limit. And now we can ask what is the effect of spin orbit coupling on properties such as the critical current of the system and the magnetization, which is now non-zero inside the superconducting state. And that is because the spin susceptibility is non-zero. So let us look at the current, the superconducting current of the system. And usually, superconducting current is just proportional to the gradient of the superconducting phase. However, now we have an additional contribution that is coming from magnetic field. Again, either magnetization or external magnetic field. In return, when we are looking at the magnetization of the system, it has two contributions as well. One, which is proportional to what usually is the current, just the gradient of the phase, and the other is regular spin susceptibility time electric field, which in regular superconductor again will be 0, but here is non-zero. Which means that if we are looking at currents inside the superconductor, they are actually carrying magnetization perpendicular to them. If we will consider vortex in such system, so we have current circulating around some area of the superconductor, it will have magnetization structure that actually resemble magnetic monopole of such system. Okay, so that is one effect of magnetization, superconductivity, and spin orbit coupling. What will be another effect is, let's look now what happened not when we are applying magnetic field, either to create a vortex or to create this kind of finite magnetization. We will be back in our free energy and ask what happens if we have fluctuation in the magnetization. So we are in the vicinity, but still in non-magnetic state, but we have quite strong magnetic fluctuation. And we will integrate them out. And what we will get is that we have the regular phase stiffness term and an additional term that look maybe a bit complicated, but if you will let me write our phase as some kind of xy spin, then this term looks like basically ferromagnetic interaction between neighboring spins and some kind of angle-dependent interaction between spins. So the first term just want to align all the spin in one direction, or in terms of the superconductor, just to create a uniform phase in the superconducting phase. And the other one wants to actually rotate them in a 90-degree angle between them. So we are getting a model that looks very similar to frustrated magnet type of model. Basically, we have a ferromagnetic interaction plus some kind of frustrating interaction. And if we are looking at the phase diagram of such system, we will see that initially, because of this competition between the two terms, we will get suppression in the phase stiffness of the system. However, above some critical value, we will have transition into a new phase. And the difference between the phases is that in the beginning we have a uniform phase with suppressed phase stiffness that turn into just chiral superconductor or helical superconducting phase where the gradient of the phase will acquire some finite value. And in between, we just have the regular disordered superconducting phase. Now, what happened in such system is that in addition to the superconducting order parameter, we have additional order parameter, and that is this kind of chiral order parameter, where the gradient of the phase acquires some finite value. And the transition in between is just a regular second order phase transition between them. Now, one may see such transition in magnetic system, where basically this kind of point, here seen in some other spin model, is what is known as the Lifshitz point. Now, what happens when we apply magnetic field in such system? So, additional magnetic field basically want to help the system already rotate in a certain direction. So first, it chooses one direction for our spin to rotate, but also it helps it rotating, and therefore, it has two types of effects. First, it kind of slightly increase the phase stiffness, and in addition, it gives us just helical phase or some gradient, finite gradient, already for very small, this zeta parameter, this kind of magnetic fluctuation term inducing chirality. And to just summarize this part, that will be our phase diagram in the presence of magnetic field. And what we see here is that the magnetic field is going to lift the transition and increase the phase stiffness of our system. So if we will look, and we can see how the magnetization will change for different magnetic field, but if we will look now at different regions and just ask how Tc change as a function of magnetic field, for example, for one parameter here, this zeta over Tc equals 0.4. So before the transition, we can see that Tc grows as a function of magnetic field. If it will be exactly at the Lifshitz point, we can see that large enhancement in the magnetic field, basically from 0 to some finite value. And also on the other side, we can see some increase in the critical temperature. Now, all what I was showing here, it looks like Tc is just going to increase and increase without actually decreasing. Obviously, it is under the assumption that the order parameter, the mean field order parameter, does not change much with magnetic field. Eventually, obviously, if you will look at the order parameter, the mean field value, as a function of magnetic field, eventually it will go down. But one can imagine to convolute these two plots and get this kind of non-monotonic behavior. And I guess I don't have more time. OK, so I will finish basically here and not continue and show you. I wanted basically to show you other systems where you can see such an effect, but I will finish it here. Thank you.
So in what way is this chiral phase similar or different from FFLO? Because there you also have a gradient of the
phase. It is FFLO.
Okay.
It is unlike in the case of magnetic field, where you are basically choosing the direction of the FFLO. Here it's just being created spontaneously, and therefore you need to be above some critical value of your parameter, unlike in the case of magnetic field, where you get it just immediately with a very specific direction.
I'm not sure you maybe flashed it, but in this helical state of the superconducting order parameter, you must have also some magnetization coupled to it because of the linear coupling. So that's also, you said you integrate out and there is no magnetic order, but here I think there should be, right?
What is here?
The helical state.
So in the helical state, you do have magnetization in the system. Yes. I mean, if you will just, basically, if I will now calculate what's the magnetization, we will have some magnetization. But it's something that is formed spontaneously in the system, and not when we are assuming that we have some magnetic order.
Is there a simple way to understand why the vortex carries this structure of magnetization that looks like a monochrome?
Yeah, let me go back to that. because I think the pictures are. It really comes from the fact that, okay, on what level? Basically, once we are, once we are looking at the free energy and we see that we have this additional term, which is allowed basically only when we don't have inversion symmetry in the system, that couple magnetization or magnetic field, let's say even to the gradient of the phase, we can see that the definition of currents and the definition of magnetization are modified. One is modified by the gradient of the phase, the other one is modified by the magnetic field, as basically we are showing here. In a simple way, we know that when we have spin-orbit coupling in the system, again, current is not only just momentum. It is modified, it's also modified by the spin. So that is, in some macroscopic way, the response of the superconductor or the current of the superconductor is also modified by something which is spin-dependent, either total magnetization or external magnetic field. And the same way, the magnetization is now also related to the fact that we have currents in the system. Each time we have current, it must be followed by magnetization. And direction is a matter of whether it's Rashba or Dresselhaus, but yeah, once you assume Rashba, then each time that you have current, you have magnetization perpendicular to it. So now you can.
For lead, spin-orbit mechanism is Rashba?
For lead is, okay, it depends, because really when they are looking at films, at thin films of lead, I would assume that that will be the most important mechanism. In the bulk, obviously not.
Since you mentioned this Gokov-Rashba paper, they predicted, as far as I remember, that you have also a P-wave triplet component. Do you have it also in your?
No. So I was assuming that I'm only looking at the S-wave component. Again, as I was mentioning before, coming from the fact that I assume that I have enough disorder that will kill the P-wave component.
So the disorder just washes out the P-wave?
Yes. Yeah, and that doesn't change if you have by the spin-orbit coupling.
Maybe one last question.
In your phase diagram, you had a sharp transition when you had from the ferromagnetic-like to the helical phase. But then when the phase boundary moved up, how do you go from the ferromagnetic to the helical phase?
Okay, so basically once you apply magnetic field, you are always in the helical, yes. So therefore, when we didn't have...
What changes as you move from the left to the right?
So basically, it's very similar to regular magnetization, like regular magnetic transition. When we don't have magnetic field, we will have sharp transition into magnetic state. When we will apply magnetic field, in the beginning, just the magnetization will follow the magnetic field, and then until the transition where you have a component which is following the magnetic field and a component which is independent of the magnetic field. So it will be similar, exactly the same here.
Well, let's thank both the speakers again.